All right, so this is the walkthrough for the arc length and sector application worksheet. So number one is just a review question. You have some arc length and sector area there. So again, as a reminder, arc length equals x over 360 times 2 pi r. Right, so in this case, we have a central angle of 120, so that's 120 out of 360. Right, times 2 times pi times 3. So you just go over and put that in your calculator for arc length. Right, 120 divided by 360 times 2 times pi times your radius. Our radius was 6. It was 3. So times 3. Round to the nearest tenth, so that's going to be 6.3 inches. Okay. And then sector area was x over 360 times pi r squared, so pi r squared. So we had 120 over 360 times pi times 3 squared. So we put that in the calculator. That's 1/3, right? 120 divided by 360 is 1/3 times pi times our radius squared. Round to the nearest tenth, so that's going to be 9.4. So our sector area is going to be 9.4. And its area, so it's inches squared. So 9.4 inches squared. Okay, and that's exactly how B and C would be along with D and E. Okay, those should be fairly quick. You don't really need to show a lot of work there. Okay, and now we get some of our application problems. So number 2, ladders can be extremely dangerous if not used correctly. A 20-foot extension ladder is placed on a wall making an angle of elevation of 85 degrees with the ground. If a person at the top of the ladder leaned back, rotating ladder away from the wall, how far to the nearest foot would the person fall before he hit the ground? Okay, so basically you have a wall here. You have a ladder leaning against it at an angle of 85 degrees. Okay, the person's going to fall. So I didn't draw the ladder very well. It's pretty steep. 85 degrees is very steep, right? Steeper than that even. Right, so there's 85. Okay, if the person leans back and the ladder falls, right, it's going to fall this way. Okay. Keep in mind the ladder is 20 feet. Right. So basically you have a linear pair or straight angle is 180. So 180 minus 185 here, or minus 85 is going to be 95. So our central angle is 95 degrees. Right, the measure of our arc is 95 degrees. I'll show it this a little bigger. And then our radius here is 20. So we're looking for the length he's falling. So we're looking for the arc length here. So we know arc length is equal to x over 360 times 2 pi r. So that's going to be our central angle is 95, or the measure of our arc is 95. So it's 95 out of 360 times 2 times pi, and then our radius is 20. The length of the ladder is 20. That's the radius of our imaginary circle. Right, all right, we have an imaginary circle, 95 degrees out of 360 times 2 pi r. Okay, we put that in the calculator. How far to the nearest foot? So we have 95 over 360. times 2 times pi times our radius of 20. That's 33.16, so the nearest foot would be 33, so he would fall a total distance of 33 feet. Right, he would travel a distance of 33 feet. Okay. Right, he'd really fall up, and he'd be in the air for 33 feet. Yeah, that's really what they're trying to ask. How long in the air would he be for 33 feet? Okay, the sprocket on a crankshaft of an engine powers the camshaft by a chain assembly. If the engine crankshaft is turning 3,250 revolutions per minute and the sprocket has a radius of 1.5 inches, to the nearest inch, how many inches of chain travel past the sprocket in 1 minute? To the nearest foot, how many feet of chain travel past the sprocket in 1 minute? So let's start with the inches, because that's what they um, give to us. Okay. So it's turning 3,250 times in a minute. Right. So we are looking for basically arc length. Right. It's rotating more and more. So our measure is going to be really, really high. But basically, we're going to use arc length here. Okay. So we need what portion of the circle? So 360 degrees in a circle, except we know we're going around that circle 3,250 times. So it would be whatever 3,250 times 360 is. But when you divide that by 360, we're just going to have 3,250. That's how many times around the circle we're going, right? It's not part. Our arc length is going to be not part of that circle, but a number of times around the circle. All right, so we have 3,250 rotations times then our circumference, which is 2 times pi times r, which is 1.5. Right, and again, if I try to explain this again, right, it's how many times around. So we're going around this 3,250 times. So one time around is 360, twice around is 720, 3 times around is what would that be? 1080, right? So basically we're going around, what are we going around? 3,250 times. So 360 times 3,250 times. The equation is really going to be 1,170,000 degrees, right? That's really your arc measure here is 1,117,000 degrees. So we would do 1170000 divided by 360. All right, which gives us 3,250. Okay, so it's really 1,117,000 divided by 360. Right? Because one rotation is 360 degrees. We have 3,250 of them. Okay, so then we can put that in our calculator. 3,250 times 2 times pi times 1.5 times 2 times pi times 1.5. Right, and that's going to give us an answer there. Okay. And then you want to do it in feet. So basically you would take your answer there and you would convert it to feet. So, well, I guess we could do this one. So 30,630 inches. To the nearest inch. So 31 inches. Okay. And if you want to convert that to feet, we do 30,631 inches, and there's 12 inches in a foot. So we would basically take that answer, multiply by 1, and then divide by 12. So we're basically just dividing by 12. That's going to be 2,553 feet. right? That's going to be 2,553 feet. Okay. All right. Peter and his partner are conducting a physics experiment on pendulum motion. Their 30-centimeter pendulum. So here's their pendulum. It swings over here. Okay, it's 30 centimeters long. Okay, the arc length is 15. To the nearest degrees, how many degrees of rotation did the pendulum swing? So we're basically finding x. So the length of the pendulum, 30 centimeters, is your radius. Okay, so you have your radius, you have your arc length. Now you need to find your central measure. So you would use the arc length formula and solve for the central angle, right, or the measure of the arc. Okay. Ashley has a sprinkler that has several varieties of coverage. The quarter circle sprinkler, right? Quarter is 1/4. Sprays water at a distance up to 20 feet from the head. What area will be covered by the spray of the quarter circle sprinkler head to the nearest square foot? So we're looking for what area, so what section or area is going to be covered. So we're going to use the sector area formula. So over 360 times pi r squared, right? But we already know this is a quarter of a circle. So a quarter of a circle is 90 degrees. So this is really 90 degrees. So it's really just a quarter, which is 1/4 times. And then we have pi, and then our radius would be how far it shoots, right? So it shoots 20 feet. So that's your radius. And then you're able to find that area. Okay. Number 6, on a basketball court, a free throw lane. So on a basketball court, it looks like this, kind of. Let me draw it this way. All right, there's the lane. Okay, there's your free throw line. There's your hoop. Right. There's the 3-point line. Okay, so there's your basketball court. So the area of this court is called the key. It's topped by a semicircle with a diameter of 12. So the diameter here is 12. Find the arc length of the semicircle. So basically we're finding this. Let me do it in blue here. You're finding this length here. So you're finding arc length. So that's the arc length formula. And then they want you to find the area as well. So you're going to have to do the arc length formula and then the area formula. It's a half circle, a semicircle, so that's 180 degrees. Right? And then your radius is going to be half of the diameter. Diameter is 12, so the radius is going to be 6. Right? And then you're going to have to use the arc length formula to find the length of that semicircle. And then the sector area formula to find the area of that circle. Okay. So that's 6. 7, Mom baked a Dutch apple pie in a 9-inch pie pan. That means it's the diameter, 9 inches across. So your radius here is going to be 4.5. Okay, she cut the pie into 6 equal pieces. That's not going to be equal. So let's try this. 6 equal pieces so that everyone gets the same size. Determine the central angle created by 2 pieces of pie. Okay, so 360 degrees around. So 1/6 of that, right? You do 360 divided by 6. That's going to give you 60 degrees. So each one is going to be 60 degrees. All right, so what's the central angle created by two pieces of pi? That's going to be 60 plus 60, which is 120. Right, determine the area covered by each piece of pi. So each piece of pi is 1/6 of the circle, so you would have 1/6 times your area, which is pi. We just said your area is going to be 4, or your radius is going to be 4.5. Right, so you would have your sector area formula as such. Okay, and then determine the circumference of the original pi. So circumference is simply 2 pi r. So that should be good there. And then if the piece of pi had an arc length of 9/8 pi, determine the area of the piece of pi to the nearest inch. So we have the central angle is 60/360. All right, we have the arc length, which is 9/8 pi. Right, so that's times 2 pi r. Okay. So you can use this to solve for r, right? You would multiply by 360, divide by 2, divide by 60. And when you would solve for r, okay, you could then plug it into the sector area formula. Right, so sector area would then be 60/360. 360 times pi, and whatever answer you have there, you would plug in for your radius, and then that would give you your sector area. Right, and then central angle for one piece of pi again would be 60 degrees. We already kind of solved that up here. Okay, so for this one, you have to use the arc length to find the radius. Once you find the radius, you can plug it into the sector area formula to find the area of the one piece of pi. Okay, so that is the 7 questions for your applications problems for arc length and sector area. Let me know if you have any other questions so I can help you.